completely finish this conversation today. We're going to talk about the actually defining experiments that were done in order to finally put to rest all the debates on carbocation structures. We're going to talk about that next week. All right. So, as always, the slides are pinned to the top, and the number of slide number that I call is the slide number in the series. So, slide number 1 is the intro slide. So, slide number 2 is where our conversation begins. We've seen this reaction before where the bromide leaves and gives us a carbocation. The species on the left is called tert-butyl bromide. Tert is short for tertiary. And it's a tertiary carbon because the middle carbon is connected to 3 other carbons. It's butyl because it has 4 carbons, and so but is the prefix for 4. And so it's tert-butyl and then bromide. It's also abbreviated to T-butyl bromide. The official IUPAC name of this is 2-bromo-2-methyl propane because the longest chain is 3, so it's a propane, and on carbon 2 we have a methyl and a bromo. IUPAC stands for International Union of Pure and Applied Chemistry. It's an organization that decides on all things chemistry in terms of nomenclature, what symbols you use for what, how do you name things, what are the official units. So they basically make the chemistry language kind of universal. So we have common names for some of the more basic compounds, but then we have IUPAC names for some of the more complicated ones. Anyway, bromo leaves, and that's a Br minus. It takes all the electrons that are in the bond with it, and so carbon ends up with 1 less electron in its outer shell, so will bear a positive charge. So what does this carbocation look like? I have represented it in a cartoon fashion, just a carbon with 3 things around it, but really, what is the geometry of this? And so we go to slide 3 and we remember maybe a similar slide back in the day when we were talking about VSEPR, the valence shell electron pair repulsion theory, that was kind of a non-quantum mechanical way of determining what the structure of a molecule is. And so I have reproduced that VSEPR chart here. And so we see that for the T-butyl cation, we have a central atom, which is E in our picture. E is the central carbon, and 3 X's around it. Those are CH3s. So, and there's no lone pairs of electrons because carbon doesn't have excess electrons. In fact, it has it's deficient in electrons. So because there's no lone pair, this ends up being a trigonal planar, whereas the T-butyl bromide that we saw, it has 4 substituents around the central carbon. All of them are single bonded, and so it's the EX4 in the picture, and so it's a tetrahedral. So based on just VSEPR, we would guess that The carbocation has a trigonal planar structure, meaning that it's a triangle. It's a triangle. The CH3s are the vertices of the equilateral triangle, and the central carbon is in the middle of that triangle. And Vesper, we said it's when electrons in the bonds and the substituents around the carbon, they push each other out because they all have electron clouds, which carries a negative charge. And so these, you get the negative repulsion. And so they all push each other out. And so this trigonal planar geometry where the bond angles are 120 degrees, that becomes the most stable structure, because that in that structure, the electrons and the methyl substituent groups are as far away from each other as possible. If I were to move one of the methyl groups, it becomes closer to one of the other ones and further away from the other, at least, or from one side becomes closer to both of them from another side. It becomes further away. It goes further away, and so basically, this is the 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 best way that Vesper tells us the structure of the carbocation should be. And so we know that we just talked about it, right? We just said that Vesper gives us the most stable structure. But we know more than just Vesper. And so on slide 4, we talk about factors that affect the stability of a carbocation. What are these factors? And just keep in mind, just keeping the big picture in mind, why are we interested in this? Why are we interested in the shape of carbocations and the factors that affect their stability? I'm not going to talk about chemists in general because, this comes into play in many different areas. But as far as really what I'm interested in and what I want to get to eventually in this series is pharmaceutical chemistry. It's like, how do we design drugs? And so we know that drugs are acted on by enzymes. And so if in the mechanism of that enzyme, as an intermediate, we form a carbocation, and we want that drug to work really well, then we create an environment around it that would stabilize that carbocation, so that the enzyme can very easily make that carbocation and make the reaction go and have the drug do its thing. So, as always, there are two factors that affect chemistry. One is steric hindrance, which basically means how crowded is the environment around the reaction site. The more crowded it is, the more difficult a reactant, a more difficult time a reactant has to reach the reaction site. It's too crowded. And so whatever is at the reaction site then will have a much longer time in existence. Longer time in existence means more stable instability. So if we make the environment around the carbocation really crowded, then the carbocation becomes more stable. Crowding is called sterics, and hindrance is hindrance. So this is hindrance to a reaction due to the crowding around the reaction site. The other factor that affects all chemical reactions, and so stability is defined in terms of chemical reactions, right? Stable thing is something that undergoes a chemical reaction at a slow rate. Unstable thing is something that undergoes a chemical reaction at a fast rate. So, so electronics also affect the stability. Electronics here doesn't mean that you have a stereo attached to it. It means where are the electrons? How can these electrons interact with other electrons in the system? And how can they interact with empty orbitals in the system? And two of the main factors that affect electronics, one is electronegativity, which is the ability of an atom to attract electrons towards it. The more electronegative atom, the more it attracts electrons towards it. And the other one is resonance. How are the electrons flowing around in the molecule? And so we're going to talk about these two, sterics and electronics, individually. First, sterics. We kind of touched on this the last time, slide 5. You may remember I put in terbutanol, which is the alcohol of tertiary butyl, meaning that you have that tertiary butyl group, but in the central carbon you have an OH group. Any molecule that has an OH group, any organic molecule that has an OH group attached to it is an alcohol. And so here T-butyl has an OH group attached to it, so it's an alcohol. And so we saw, so on the left is the stick figure model of T-butanol, and on the right is the space filling model. And basically the point here was that we don't see the central carbon, right? It's buried inside of all those methyl groups. And so below it, that was kind of review from last week. Below is an analogy to T-butyl cation, meaning that we're kind of looking at the same things. And so if I build a stick figure model of this, it's going to be trigonal planar. In the middle, I have the molecular kit model of it. Anybody who's gone through organic chemistry knows a molecular model kit and loves a molecular model kit. You can't really survive organic chemistry without it. I still have the molecular model kit that I used when I took organic chemistry in 1986. So it still comes in handy. Anyway, so in the molecular model kit, we see that we have the central carbon and the 3 methyl groups around it, and the extra p orbital. That's the empty p orbital. It's empty because it's a cation. The more important thing is the one on the right, the space filling model of this carbocation, and we see that where's the central carbon, right? Nobody can see the central carbon. It's very difficult to access. You have to kind of work your way through all of those hydrogen groups and the carbon groups to which they're attached in order to reach the middle carbon. Not that it doesn't happen. It happens in a blink of an eye, but it happens a lot slower than if those methyl groups weren't there. Any questions on the sterics before we go forward? All right. So on slide 6, we're going to start the conversation on electronics. This is again what I have here is a review of the talk that we had on resonance many years ago. So what I have shown here is a carbon-carbon double bond on slide 6. A double bond, one of the bonds is a sigma bond, which is formed from the overlap of sp2 hybridized orbitals, and so it's a one lobe overlap with one lobe that forms the single bond, and it's a sigma bond. But then we have p orbitals that are not hybridized, and so therefore they look like what a p orbital would look like on both carbons, and they also overlap. And the top area overlap is the bonding orbital, the yellow one, and the blue one is the antibonding orbital. We have talked about those. We'll talk about them later. For now, it's not really important. Just to know that we have orbital overlap above and below the plane of the molecule, and that forms the second bond between the carbon-carbon, and that's a pi bond. It's pi because it's formed from the overlap of p orbitals. Sigma is sigma because it is formed by the overlap of s or s-like orbitals. So what happens if, like on slide 7, I add another ethylene group at the end of this? So we'll see I have 1 and 2, or carbons 1 and 2 are one ethylene group, and carbons 3 and 4 are another. This is called a 1,3-butadiene. It's a butane for carbons. It has double bonds, so it's a ene. It has 2 double bonds, so it's a diene. And where are the double bonds? They're starting on carbons 1 and 3, so it's 1,3-butadiene. So each one of these bond between C1, C2, and bond between C3 and C4. They're basically just like the bonds on the ethylene group that we saw in slide 6. However, why can't we have overlap between the p orbitals on carbons 2 and 3? And in fact, we do. So if we go to carbon 8, we'll see that we do have evidence that this molecule could exhibit polarity, and that the electrons are basically free floating through all of these p orbitals. And so if we go to slide 9, we see that we can draw 4 different structures with different double bonds and single bonds in between carbon atoms, different carbon atoms carrying the plus or the minus charge. And so the electrons here are completely delocalized, meaning that they're not localized to just the double bond that they were in. They're delocalized over the pi system, the system that is developed by the overlap of the p orbitals. If we were to get a crystal structure of this 1,3-butadiene, we would see that the bond lengths 1, 2, 2, 3, and 3, 4 are identical, and that the carbons at the end carry a partial negative or partial positive charge characteristics. So we will see all of those in both crystal structure and in spectroscopy. We could see that carbon-carbon bonds are all of the same length, and this we call this a conjugated system. Conjugated means that the two double bonds are conjugated to each other. They're mixed in with each other. They overlap, and so in a conjugated system, the electrons are delocalized. So conjugation leads to delocalization. You will hear those terms applied to this concept over and over again. One of the most famous molecules that does this conjugation and does it in a very special way is benzene, which is C6H6. It's a ring, and as you see, I can draw the double bonds either based on the structure on the left or based on the structure on the right, and those can interchange. So those two are called canonical structures because they follow the canon of single bonds and double bonds. But canonical structures don't actually exist. They're a figment of our imagination. It is a way for us to show a conjugated system using the model of sticks and elements that we have here. So for a conjugated system like benzene, we represent it as the structure on the bottom right, that we just put a circle in there, meaning that the electrons, we know that the electrons are free floating over all 6 carbons. And again, both spectroscopy and crystal structure shows that all carbon-carbon bonds are identical, and all hydrogens in this molecule are identical. So all hydrogens and all carbons are identical, and all carbon-carbon bonds are identical. If one of the canonical structures were to exert more influence, then we'll see the bonds would alternate longer, shorter, because double bonds are shorter than single bonds. But we don't see that. We just see one type of bond, one type of carbon, and one type of hydrogen. So it makes us pretty confident that this resonance structure that we have written on bottom right is representative of what is actually going on. So if I go back to slide 9, the 4 structures that have double bonds and single bonds, those are the canonical structures, and the one at the bottom, that's the resonance structure, the conjugated one. So why am I talking about this? It's because resonance doesn't have to happen between double bonds and atoms that all have free p orbitals. So if we look at slide 11, we see that the carbon-hydrogen sigma bond of one of the methyl groups of the T-butyl cation, that can overlap with the p orbital of the central carbon. And so we can basically then form as one of our canonical structures the one that we see on the bottom right, that there's a carbon-carbon double bond and there's an H plus floating about. As I said, this is not an actual structure. What this structure tells us is that those methyl groups can donate electrons to this carbocation and remove the positive charge from the carbon, and put it on hydrogen. Even though so far we've been saying that carbon and hydrogen have the same electronegativity, that's a rough approximation. Carbon is more electronegative than hydrogen, even though the difference in electronegativity between them is less than the difference in electronegativity between any other two elements. But still, carbon is more electronegative, and so hydrogen can better tolerate carrying the positive charge. What does this mean, having these? It means that in the actual molecule, the carbon-carbon bonds are shorter than single bonds. So they're somewhere in between a single bond and a double bond. And it also means that the central carbon isn't carrying all of the positive charge. The positive charge is dispersed over 9 hydrogens and the central carbon, so over 10 atoms. In one of the early lectures, we said that dispersal of charge is one of the principles of reaction chemistry. That is, you want to find stability, look for something that disperses the charge more than other things. So we want the charge to be dispersed as opposed to concentrated in one point. Concentrated in one point is energetically unfavorable, whereas when the charge gets dispersed over a whole bunch of stuff, then it becomes energetically favorable. So we're going to now apply this principle. So first of all, before I move on from this slide, this cartoon also explains why carbocations, T-butyl carbocation is stable, and how do these electronics in the molecule affect the stability. It also shows us that our guess at the beginning that this carbocation is a trigonal planar molecule makes sense, or at least is consistent with the experimental results that we get here, which is what? Which is carbon-carbon bonds that are shorter than a single bond and hydrogens that are more acidic than normal methyl groups. We have those experimental evidence, and that is consistent with our theory of the structure of the carbocations. So we now go to the last slide here. And last week we talked about that, well, tertiary carbocations are the most stable, primary carbocations are the least stable. Why is that? We can now talk about that stability through not just sterics, but electronics as well. So on the top, I have the ethyl cation. So methyl cation, I'm not even going to talk about CH3, because that doesn't have any neighboring groups that can donate electrons into the p orbital of the central carbon. So a methyl cation, which is CH3 plus, that is incredibly unstable. Why is mercury poisonous? Because mercury can get in the middle of the CH bond of methyl groups. And so what you end up with is methyl mercury. That is CH3 Hg. And that is highly reactive, right? So it's now going to go methylate everything that it sees, your DNA, proteins, your cell structure, everything, and it's going to kill you because then the proteins and the DNA and stuff don't function the way they should. So that stability of a primary cation is what explains that. So ethyl cation is a primary one, meaning that the carbon that carries the positive charge is attached to only one other carbon, a methyl group in this case, because we're talking about methyl donations. And so here I can only draw three structures. These are called hyperconjugated. Normal conjugation is when p orbitals overlap. Hyperconjugation is when we have electron donation from a sigma bond into a p orbital. So I can only draw three hyperconjugated structures. In isopropyl cation, which is secondary, that is, the central carbon is carrying a positive charge, and that central carbon is attached to two other carbons. Now you can say I can draw six hyperconjugated structures, three for each methyl group. So in ethyl cation, I only have one methyl group, so I have three. In isopropyl, I have two methyl groups, so that's six. And it's T-butyl, which is a tertiary, I have three methyl groups, so I can draw 9 hyperconjugated structures. Meaning what? Meaning that in a T-butyl cation, my positive charge is dispersed over 10 atoms. In isopropyl, only 7. And in ethyl, only 4. Electronically, then, I would say ethyl is the least stable, followed by isopropyl, and the T-butyl is more stable. That's from electronic point of view. From sterics, of course, ethyl only has one other methyl group attached to it. It's free and clear. Isopropyl has two other ones. This is sterically hindered, but not as bad as T-butyl, which has 3 methyl groups attached to it. So sterically also, we get the same ordering, that ethyl is least stable and T-butyl the most stable. So electronics and sterics both lead to the same conclusion, and that conclusion is borne out by experimental results as well. So when we look at the reactivity of these carbocations, we see that ethyl cation is the most reactive and of these three, and T-butyl cation is less reactive. One just comment on historical perspective on this is that if you were to take organic chemistry in 1965, you wouldn't learn about any of this. A lot of the preliminary work in this area was done in the 1970s, early 70s. And a very interesting thing is that two very famous chemists, one was George Olah at Case Western Reserve in Detroit, and the other one was Harold Brown at another university in Detroit. I forget which one. They got into an argument about the structure of these carbocations. George Olah in 1977 went to University of Southern California and basically devoted the entire 1980s on on the debate that he had with Herbert Brown. Herbert Brown had already won a Nobel Prize for his work in boron chemistry, and there are a lot of historical articles written on this debate because it was a very important debate. And then finally, in 1989, George Olah came out with a series of papers that basically shot Herbert Brown out of the water. And in '94, Olah won the Nobel Prize for that. So basically, these things about stability of carbocations and this and that, this is all late '70s, early '80s. So it's not that long ago. Grad students who worked on this are still alive and well and working. Anyway, that concludes what I wanted to say about the structure of carbocations for today. So next week, Shamash, I lied to you. I said I'm going to talk about chirality, but that's going to happen next week because now the question is really from a chemical reactivity point of view, how do we know that this carbocation has this trigonoplanar structure? And so we're going to talk about chirality and racemic mixtures and enantiomers and the reactions of carbocations. Hope to see you then. All right.
I'll be
Yes,
there. Thank you very
Case
much,
Western
Sam.
Reserve is in Cleveland. Yes. They're all mistakes by the lake. Sorry, that was my West Coast prejudice. What, Shamash?
No, just saying thank you and see you next episode. That's it.
Any questions? Anybody wants to come up to discuss carbocations or other points of interest in chemistry?
Okay. So to go over some of this, some general questions, maybe before. So for carbocation, like surrounded by bulky groups, uh, is that, so does that mean it generally reacts faster?
No,
With
reacts
nickel.
first of all, pronunciation is carbocation.
Oh, thank.
Yeah, so that's an extremely common mistake. So I think every first year organic chemistry student who reads that chapter first says carbocations, and the professor has to correct them. So yeah, when they are when it's bulkier, then think of it as when it's bulky, reagents can't get in there, so it sticks around longer. So if it's bulkier, it doesn't react as fast because reagents can't get in there, have a difficult time getting in there.
Okay, yeah, carbocation. Okay, yeah. So yeah. I don't have a degree in chemistry, obviously. Like I said, this is one of my first. Great to catch this. Um, but well, okay. So going over some of the slides, doesn't it suggest that a crowded carbocation is more stable because it's harder for reactants to approach? So is this a question of kinetic stability? Did I
Yes.
get that right, or thermodynamics? Okay.
The at this stage, this is kinetic stability because we're not thinking about the thermodynamics of the product that we get and compare that with that of the reactant, because necessarily, I would even say, the product of the reaction of anything with a carbocation is going to be energetically a lot more favorable than the carbocation itself. So it's not the thermodynamics, it's not the stability of the products and reactants, the comparison of that. Instead, it's the activation energy. How much energy do you need to bring these two together for the reaction to take place? And so that's a kinetic analysis, not a thermodynamic analysis.
Oh, okay. Okay. Yeah, so okay, also with okay, so conjugated uh cation, see I believe I got that right. Dean-cation.
Now,
Um
cat, go cat, ion,
oh,
right?
oh,
So
okay.
ion is ion. Cat comes from cathode. So it's the cathode ion. So it's a cat ion. Cation.
Okay. Okay, cat iron does let's see. Does that stay at is the positive charge stays on one carbon only, or the conjugation allows the positive charge to delocalize over several carbons? Um,
Yeah, the conjugation allows for the part of the positive charge to be borne out by the hydrogens, as opposed to all of it being borne out by the carbon. So you basically spread the positive charge instead of all being on one point, which is the central carbon. You spread it over a number of hydrogens and that carbon. So that becomes more stable. Hi, Joe.
oh,
Welcome to the
uh,
stage.
oh, yeah, okay, and let's see another question that I'm learning, like conjugation and resonance are related concepts. I know that much. So how would you explain the difference between like a simple like a simple resonance stabilized cation, or
So
see, I can't even pronounce.
resonance is what happens. Conjugation is the structure. So in a conjugated system, you get resonance. So conjugation means that you have alternating double and single bonds, and so the orbitals conjugate. Resonance means that the electrons that you have are free flowing through your conjugated system.
Okay, and see, would you get like any extra stabilization from extending that to a system by one more
Oh
like
yeah.
double bond?
No. You can add acyl groups, amine groups. You can put all sorts of substituents up there
Sam, one
too.
of the most common ones I'm familiar with these are you add nickel and then you add hydrogen. So you do a catalyst and then you add hydrogen. So you break your double bonds and you hydrogenate your carbon chain.
Right. Absolutely. That's a very common industrial use of hydrogenation. Yeah. Uh, yeah. These you as I said, it's the job of the chemist. So once they figure out what the mechanism of the reaction is, depending on if they want to slow down or speed up the reaction, to kind of play around with these substituents to come up with what they want. Uh, Either this Monday or the Monday after that, I'm starting the pharma series. That basically is how do pharmaceutical companies come up with drugs, and how do they get them approved? So we're going to go through that, and one of the things that we'll see is structure activity relationships, or SARs, and that's when you kind of keep in a series, you change substituents around the carbon of interest to see how that changes the activity, and then that helps you design your molecule. And all of that is basically stabilizing, or in the case may be destabilizing the intermediate or the transition state using these electronics and sterics tricks that I just talked about.
There's another fun one I'll say that I ran across in the industry that we wanted to inhibit. When we had a polymer chain and we were making kidney filters, the membranes for kidney filters, occasionally in the raw mix of that plastic, you have hexamers, basically. It was a molecule that has a 6 carbon chain, and it's in a ring, and they can end up crystallizing in plastics. So if they are together, um, they end up isotropically like attracted to each other and then crystallizing. And so one of the rumored myths always to break this interaction was to add a little bit of water to your plastic mix, because then these um, bonded pairs that were available on this hexamer were interacting with water. And so water ended up preoccupying the surface site, making the fouling or crystallizations inside of the mix no longer relevant.
That's a great example of using the difference in kinetic speeds between uh, between two reactions. So if you have an unwanted reaction, you add something else that more rapidly reacts but won't change the composition. Here, this is interaction with water is a much more rapid interaction than the crystallization. Even if crystallization would be more energetically favorable, uh, if you can kinetically prevent that, then by the time thermodynamics becomes an issue, you have isolated your product and you're out of that reaction mixture.
The ultimate formation of those membranes was made by precipitation, where they were soluble in a solvent, and then as you added water at a certain surface at a boundary layer, the water porosity ended up uh, taking away the solubility, and the plastic would fall into these columns of creation, and that's what would create this size of which molecules are allowed to go through this plastic membrane or not in water treatment or in blood treatment.
Yeah, now we're getting into macropolymer chemistry, which I know very little about. So sorry. That it's a fascinating thing because you end up doing kind of ion exchange columns in addition to filtration all at the same time, and that's all really fascinating to me. but unfortunately, I don't know much about it. If Dave was here, my friend Dave Coons, he would have been all over that because uh, he is an analytical chemist and worked for decades at 3M making sensors and filters.
Okay, and to go over some more, so some factors that contribute to these are, see, are these right?
Sorry, say that again.
Substitution.
I kind of missed.
I'm trying to look over some review factors. Like, are these factors correct, Sam? Like, substitution, hyperconjugation, resonance, and medium. Or are those some of the those are some of the main factors that contribute to these structure reactivity?
So at the end of the day, only two factors affect reactivity: sterics and electronics. And that's, if you look at slide 4, I've put that really uh, in the context of what we were talking about today. But that's a very, very generic statement that I really can't think of an organic chemistry or biochemistry question that these two are not the factors. Everything else falls into either electronics or sterics. So you see, electronics, I put in electronegativity, I put in resonance, concentration, Joe. That also is if you want to really think about it, it's a steric thing, because by having more of it, you now are kinetically overcoming the steric hindrance. So increasing the concentration is a way of overcoming steric hindrance. If sterics is an issue for you.
If it's
So
the rate limiting, right?
yeah. Yeah. When you're talking about kinetics, you're only talking about the rate limiting step in the reaction, because the rest of them don't don't come into
I
the rate law.
I love to use the example, and I've said this many times, is um, the truck that it takes to bring the video games to the store before the
Yeah.
video games are sold is not really statistically relevant in the rate of how the video games get sold unless the shelf goes empty. At that point, then it becomes an impact.
So it doesn't impact the number of video games being sold. The number of video games being sold, that's a thermodynamic argument. The kinetic argument is how fast can you get the video games to the store for them to sell? Because if you imagine the store is completely filled to the rim with video games, they still sell a set number of uh, video games. That's when kinetics is not an issue. But if as soon as the video game hits the store, I mean there isn't any, and as soon as it hits it, they buy it, then the speed by which they get to the store becomes the determining factor. Whereas before, it's how many people are interested in the video game that's going to be determining it. That is a really good example of. I was kind of expounding on your example, not refuting it. It's a really really good example to understand this. I like that. Hello, Nathan. Hi, Ben. Didn't see you up there.
Hey
You have
Sam,
the
sorry,
floor.
it takes a surprisingly long time to unlock your phone and
Yeah.
unmute. Yeah, thanks. I'm enjoying it, listening in.
Nathan, do you have questions?
Yeah, I was just curious, Sam. Like, thank you very much for doing this still. I'm super happy that you're still running chemistry rooms. But I was trying to go on my own over the last 4 months to do a primer and catch up to where you're at with chemistry. And I'm really at the bottom floor. Is there like a go-to book that could expedite like my ability to learn fundamentals chemistry to start to keep up with you guys? Or do I just need to go take a university class and just get browbeated by learning the vocabulary in order to like get further and deeper into chemistry?
Well, how serious are you about?
Unfortunately, I can't practice it. I'm 45 and I'm a carpenter, so I'm not going to be able to switch gears at this point. But I'm pretty serious about it. I think I want to fill the rest of my adulthood with it. So
So, I don't know. I don't know a book that can do that for you, but a really, really easy way to within 2 years get to where we are and way beyond where we are is to go to your local community college and take the first year of general chemistry and second year of organic chemistry. Then at that point, you will know, most of the chemistry that you need uh, in your daily basis, and you will be able to because you get enough of the analytical chemistry, enough of the physical chemistry, enough of the other stuff that you would actually be able to understand what people are talking about.
cool.
But
Thank
that's
you.
yeah, but that takes a little bit of a commitment because these are semester courses, 2 days a week, 1.5 hours of lecture, and 4 hours of lab. So you're 5.5 hours twice a week uh, in class for these.
Well, I mean, I appreciate the guidance. I don't know if I can actually execute that relative to having the ability to live, but I'll give it a
Yeah.
shot, and I won't
It,
waste too much time just trying to like pick up a
if
book and not getting anywhere.
in comparison to that much of class, if you want a really expensive book that will talk about almost everything chemistry, Harry's Chemical Engineering Handbook. It's a couple reams of paper
I don't think chemical engineering approach
versus chemistry.
versus chemistry approach because uh, uh, chemistry approach is pictorial. It's you think about molecules, you think about atoms, right? You picture them how they're reacting. But chemical engineering is math. So basically, you don't get a conceptual understanding of chemistry. You get a mathematical understanding of chemistry because the job of the chemical engineer is not to do chemistry. The chemist does the chemistry in the lab and then gives that to the chemical engineer and says, make 15 tons of this a year. I've made 3 milligrams of it. Now you make 15 tons of it. So now the chemical engineer has to worry about heat transfer, has to worry about, solvation rates, has to worry about steering rates, all where the pipes are going to go, how are they going to do the mixing. So chemical engineer approach is to that, not that, okay, uh, what is going on with the structure of the carbocation in the rate limiting step of this reaction. That is done by the chemist in the lab.
I would say some chemies like to get into rate limiting. It was the most beautiful math I've ever seen is rate laws. It's really pretty math. But you're right. As a chemical engineer, I'm speaking to the math, not the something else.
Well, I really appreciate both of them, guys. Sam, I'll definitely look into the community college thing. I think that's probably the way I'll go. But what was the book again? Henry's something?
Here, I'll put it in chat. It's Perry's.
Harry's. I'm gonna get off the stage, Sam. Thank you so much for doing the chemistry stuff, mate. Really appreciate it.
Sure. I'm glad you're getting something out of it. Beautiful math means elegant, meaning
It means that
you,
every statistical regression turned out to be a linear equation,
yeah.
ultimately. We would end up doing design of experiments, we would have ice tables, we would end up having degrees of freedom analysis, and then we would finally have a model, and only then would we do any statistical regression.
Any
I
other
think
questions?
is it technically possible that you can actually calculate the rate and show the math between an iodine clock?
Oh yeah, absolutely,
All right. So that's
absolutely.
kind of a really good example of
Yeah. No, that
unpredictable.
math has been worked out to the level of elementary school because my wife and I used to do the monthly science night at my kids' elementary school, and so we would have experiments for them to do, and then I would do a presentation, and I used to do the iodine clock as one of the presentation. It's awesome if you're a good storyteller. That iodine clock it makes for a really really good show. And so yeah, you can talk to a fifth grader about the math of the iodine clock in a level that they can understand.
We used an iodine clock with a limiting reagent, um, so that way it was never a back and forth reaction. It was more like a limiting reagent. And as a car rolled forward, it added a little bit of the reagent. And the point was on the day of competition, you're given the distance of a vehicle, and then it has to learn where to shut itself off. So it was a prediction in chemistry using stoichiometry of how far does the car go before you tell it to stop, and the closest one to the line is the winner.
Oh no, 5 seconds at dead space. Okay. This. Yes, there are no more questions, and so thank you all for being here. I really appreciate your participation in these rooms. Makes it worthwhile to put these together, and so I thank you. I am going to, Shamash, I don't know if you want to turn off the YouTube because I'm going to play us out with a copyrighted song. This is